Video on the single and double displacement reaction Prelab for Chemistry 10. So in this particular lab, our goal is to first observe the different types of chemical reactions and the signs of chemical reactions, and then also to write the actual chemical equations and balance them according to the rules you learn in lecture, and then to figure out what products are formed in each of these chemical reactions. So one of the things to note first is just what are the different signs that a chemical reaction has taken place, and there's several of these that are listed in your lab procedure, and I'm just going to walk through these signs with actual pictures. So the first two pictures here show the formation of what we call a precipitate or solid. Okay, so a precipitate is basically a tiny particle, but they're solids that appear, and the typical appearance that you see when a precipitate forms is that it's cloudy. So the solution looks a little cloudy or opaque, meaning that you can't see through it. So contrast these two solutions, which are the reactants for the reaction, and then once they're mixed together, look at the appearance of that cloud. So that cloud is the precipitate, and that's the product that's formed as a result of the mixing of these two solutions. So these two solutions are transparent. We can see through to the other side of the test tube where there's that black background. And then with this one, we can see that that black background is not as clear now because it's obscured by these small particles or precipitate that's blocking our view. Same thing here, you can also get a precipitate formation by mixing a solid and a liquid or a solution reactant. So in this case, when we mix the two of these, we see that actually the solid appears on top of the solid reactant. So there is what we call a deposit showing up over the original piece of metal that was being reacted. A second type of sign that we often see with chemical reactions is the change in color. So again, here I have two pictures that show the change in color that appears when we have two different solutions that are mixed together. So here's a solution that is a little bit light orange. Here's a solution that's clear, transparent, and you can see that both of these are transparent solutions. We can see through them. And when we mix these two, you can see that it forms this darker orange color, which is the product that's being made as a result of the mixing of these two reactants. We can also get a change in color when we mix a solid or a metal with a solution. Here's an example of that. I mix these two reactants together, and what I get is a blue solution. So obviously the metal in this case has completely dissolved in that solution. A third sign of a chemical reaction is the production of a gas. And a gas is really easily observed because you can see bubbling occurring. So you can see bubbles at the top. A lot of times you'll see bubbles appearing inside the solution as the gas is being formed. Gases are less dense than water, which is most of the solvents used in these reactions. So because they're less dense, they're going to escape to the top of the solution, and therefore you see these bubbles just go up to the top. You can have gas being formed by two solutions. They're mixed together, just in this case, or you can have it from a solution and a solid that's mixed together and forming a gas here. Another common feature of a reaction is a change in temperature. So this particular one is showing you the temperature of each of these solutions before they were mixed together. You can see that the temperature is right around 25 degrees, but once they're mixed together, there's a change in the temperature. Now it goes up to almost 30 degrees Celsius. So that tells you that there's a heating up, in this case, of this reaction. So this is an example of an exothermic reaction. You might see a reaction where when you mix them together, the temperature actually decreases. Let's say this goes down to 20 degrees Celsius, for example. So there will be a sign of an endothermic reaction. In this lab, you're going to see both single displacement reactions as well as double displacement reactions. We learned about these in lecture, but I want to repeat again here that single displacement reactions are reactions where you have one element reacting with an ionic compound. So the formula of the element can be represented as A. Formula of the ionic compound is represented as BC. And what ends up happening is the element displaces or kicks out the cation in the ionic compound, making B, which is the element form of the cation, and then a new ionic compound, which is AC. Okay, double displacement reaction is fairly similar, except that you have two ionic compounds instead, A, B, and CD, and then the reaction is basically a swapping of the two cations. So the cation for this one moves to this one and partner up with D, forming AD, and then the cation for this one, which is C, forms a new ionic compound with B, CB. For double displacement reaction to be considered happening, you have to have product that is either a solid, a liquid, or a gas. So we have these two tables that's included in your lab procedure that helps you figure out whether a reaction happens or not, and one of these is called a solubility rules, which tells you what kind of ionic compounds are soluble and what kind of ionic compounds are insoluble. So if it happens that one of these ionic compounds that you make in your product is a solid, then you know your double displacement reaction has taken place. The activity series, which is the other table you see here, helps you determine whether the single displacement reaction can take place or not. To use this series right here, you're going to need to look at your A and B elements right here. So if your A element is higher in this series compared to the B element, so for example, let's say lithium versus magnesium. So if my A here is lithium and my B here is magnesium with an anion, let's say magnesium chloride, then there's going to be a reaction where now what I get is magnesium and lithium chloride. Okay, so hopefully that makes sense there. Only element with higher activity can displace element with lower activity. If you swap that out and you have magnesium with lithium chloride, then you're not going to get any reaction because magnesium is lower in the activity series compared to lithium. So what you have to do for the lab is really observe whether a reaction has taken place or not once you carry out the reaction, the mixing of the two reactants. And then you need to write the reaction and make sure you balance it. So you got to write the reactants, you got to write the products, put an arrow between them, and then balance the equation, right? Again, to determine whether a reaction occurs or not, you're going to look at one of those signs that I mentioned earlier, and then at the end, make sure you include the actual states of matter. So if you form a solid, then there has to be an S on the product. If you form a gas, there has to be a G. If you form water, water exists as a liquid, so there has to be an L next to it, okay? All right, so that's the reactions pre-lab, and now I'm going to show you an example of how to complete your reactions pre-lab with one reaction example. Okay, so here I just want to show a quick short movie on how the reaction of sodium mixed with water looks like, and this is actually going to be 3 different alkali metals, but we're going to focus specifically on just first lithium and then sodium and then potassium, but we're going to look at one of them just to kind of observe what happens during that reaction. So the first thing to notice is that there's a beaker here, and the beaker has water in it, and in each one of these beakers we've added what we call an acid-base indicator, which is a substance that will turn a different color when you have an acid versus a base. As it happens with this specific indicator, it is colorless when it is acidic, and then it will be pink when it is basic. So what we're going to do is then add a piece of the metal of interest, and then we're going to see what happens. So you can see the addition of the metal here causes the solution to turn pink, which tells you that a base has been created, right? So you got to think about then as you're writing this, what base can that possibly be? And then the second thing you notice is that there's some kind of a gas. How do I know there's a gas? Well, there's a little bit of a smoke there that's being generated as that reaction is occurring. The metal is slowly being dissolved into this water, and there's a gas that's being produced. So when I write my reaction, I'm going to have to consider both of those ideas in mind. Okay, so let's take a look at how we can write the reactions that we just observed. So we mix a piece of metal, sodium, with water, and what we observe is we see a base and a gas being formed as a result of it. So our reactants are sodium, metal, and liquid water. So So the first thing we need to do is just write those reactants in the correct form. So here's our sodium metals, Na in the solid state, right? Because that's what we put in. And then water in the liquid state is just H2O with an L next to it. And then we have to write our arrow to figure out what our products are in this case. This could be either a single or double displacement reaction, as we said earlier. So noting that this is really a element on the one side and then an ionic compound, if you want to think about it that way, on the other side, then this is really a single displacement reaction, which has the form A plus BC going to AC plus B. Now, H2O is not your stereotypical ionic compound. In fact, it's not an ionic compound at all. It's a covalent compound, but it turns out that acids and water are one of these compounds that can actually form a number of ions when they are in that liquid or in the solution state. So it turns out that with water, it could break apart into two things, which is H plus and OH minus. So I'm writing water as H plus OH minus here to illustrate that idea that H2O can be written as this form of the BC, which is the ionic compound, right? There's a cation, there's an anion. The reason I want to write it that way is because then it helps me figure out what the product should look like. The product should be A with C combined together. Well, our A here is sodium and our C here is OH minus. So then we think about, well, what's the ion that's formed by sodium? Well, it's sodium plus. So then the formula of the product is going to be NaOH. That's the AC. And the B here is the element form of our B in this case, which is H plus. So we have to think about what is the elemental form of H. When hydrogen is found as an element, well, it exists as H2. So we have to write it as H2 in this case. So we're almost complete here. The only thing we need to do is first balance it out. If we want to balance this correctly, it will require us to put a 2 on this side, 2 on this side, and a 2 on that side. And that should balance out our equation. And the last step is to include the states. Remember, we noticed two things that were formed, a base and a gas. The gas is easy. That's going to be our H2. We remember from the periodic table that H2 exists as a gas. The base must be NaOH because as we learn, OH, anything with OH is a base. And since this is all existing in water, we're going to put the symbol AQ there, which indicates that it's a solution that's dissolved in water.